The San Francisco estuary is the largest on the Pacific coast of the Americas and encompasses nearly 500 square miles of water, draining 65% of California's rain and snowfall, and serves as the primary habitat for over 1,000 distinct species of fish, mammals, and invertebrates. Over 1 million birds use this specific body of water as a central hub during the winter. It is a mandatory stopover for wildlife migrating along the Pacific Flyway. But beneath the surface, the geography shifts. When we pull back the water layer on a bathymetric map, we see that 2/3 of this massive expanse is less than 18 feet deep, dominated by vast, shallow mudflats. Overlaid directly on top of these shallows is the commercial shipping grid. Deep draft cargo vessels have to thread through a specific set of narrow trenches that cut across the mudfloor. Moving massive ships, many carrying millions of gallons of heavy fuel oil, through these tight, shallow choke points leaves no room for error. Operating heavy industry inside a fragile ecosystem requires an overlapping network of physical dredging, active traffic control, and human governance. This makes the success of every vessel transit a prerequisite for the survival of the species that inhabit these waters. The first hazard to navigation is the bay floor itself. Because it acts as a natural drain for California's river systems, the estuary is a massive sediment trap. Silt constantly accumulates, filling in the deeper natural channels. To keep the ports operational, the U.S. Army Corps of Engineers has to physically alter the baybed. Every year, they dredge roughly 5 million cubic yards of sediment from the floor. Looking at the geographic limits map, we trace the main ship channel. Maintain that 55 feet, it's the required entry for Pacific vessels. Inside the bay, corridors tighten. The Pinole Shoal Cut is just 600 feet wide. Pilots calculate underkeel clearance, the vertical distance between the ship's hull and the channel floor. Offshore, ships maintain a clearance of 10% of their draft. Inside the bay, this compresses. Massive tankers are permitted a clearance of just 2 feet. If a vessel drifts outside the dredged channel limits or miscalculates the tide, the hull strikes the mud, halting thousands of tons of momentum. Dredging establishes the physical boundaries of the channel. Without it, ships would exceed the navigable depth, leading to the groundings that precede a major oil release. Dredged channels provide a stable path, but they are subject to volatile atmospheric hazards. The bay generates intense weather. In the summer, temperature inversions pull fast-moving sea fog directly through the Golden Gate. In the winter, cold land masses react with moist air to create dense, slow-moving tule fog that zeroes out visibility. Below the fog, the water is volatile. The Pacific Ocean forcing its way through the narrow Golden Gate creates complex currents and intense local eddies. To calculate their exact drift, shipmasters rely on a sensor network called P.O.R.T.S, the Physical Oceanographic Real-Time System. This network feeds live tidal and current data directly to the bridge, allowing pilots to adjust their heading minute by minute. When the fog rolls in and visibility drops below half a nautical mile, visual piloting fails. Crews have to transition to electronic instruments to stay inside the dredged cuts. This requires technological intervention at choke points. Because standard radar simply shows a bridge as a solid wall of concrete, engineers install radar beacons on the center spans. These transmit a distinct coded arc to the ship's display, identifying the safe passage between the physical abutments. Real-time sensor networks and radar markers give pilots the actual capability to stay inside the channels when the environment turns hostile. Even with a clear path and reliable instruments, a 600-foot wide channel forces cargo vessels into close proximity with ferries, tugs, and barges. Preventing ship-to-ship collisions requires a central authority. That authority is the Coast Guard's Vessel Traffic Service, operating out of a central command center situated on the high ground of Yerba Buena Island. VTS operates a vessel movement reporting system. By integrating shore-based radar and automatic identification system data, they track every power-driven vessel over 40 meters moving through the bay. Operators exert 4 escalating levels of control over this traffic. They monitor movement, inform vessels of hazards, recommend navigational changes, and, when an immediate threat is detected, direct specific ship actions. This control extends to stationary ships. Vessels waiting for berths or transferring cargo must park in designated zones, like Anchorage 9. To prevent deep draft ships from swinging into each other during tidal shifts, VTS enforces strict spacing. Every anchored vessel is required to maintain a 750-yard radius from its neighbors. By acting as the region's central nervous system, VTS organizes chaotic, multi-use traffic into a predictable grid, keeping heavy assets safely distanced from one another. The final layer of harbor management is the regulatory framework that governs human behavior. Following a major tank ship spill in 1990, the California legislature passed the Oil Spill Prevention and Response Act. This mandate created the Harbor Safety Committee to oversee the waters of the San Francisco Bay region. The committee brings deep draft pilots, tug operators, the Coast Guard, and recreational boaters to the same table. Together, these stakeholders establish localized best practices, reconciling the conflicting needs of everyone sharing the waterways. They establish protocols for calculating the required bollard pull for escort tugs, mapping out safe routing for passenger ferries, and keeping kayakers out of the commercial shipping lanes. Their most critical guideline deals directly with visibility. The committee explicitly advises that if visibility drops below 0.5 nautical miles, vessels should remain safely docked. Protection of the bay relies on this negotiated consensus. The dredging and the sensors only work if the human operators obey the established limits. On November 7, 2007, these operational protocols were put to the test. The MV Costco Busan, a loaded container ship, struck the Bay Bridge, tearing a massive gash in its port bow. On the paper chart, physical and technological layers functioned properly. The course line was plotted to pass between the Delta and Echo towers, and bridge raycons transmitted accurate data. Yet the ship drifted south of its track, heading toward the tower abutment. The environmental conditions were severe. The ship was moving at over 10 knots through thick fog, with visibility falling below a quarter of a nautical mile. The failure began in the human layer. The pilot ignored the Harbor Safety Committee's guidelines, deciding to undock in dense fog instead of waiting for visibility to improve. On the bridge, resource management broke down. Language barriers between the American pilot and the Chinese-speaking crew meant critical information about the radar was never shared, preventing the crew from challenging the pilot's errors. As the vessel deviated from its sailing plan, VTS operators remained strictly at the inform level of communication, missing the opportunity to issue direct orders to halt the ship. The accident proves that when human compliance fractures, it neutralizes every physical and technological safeguard in the estuary. When the Costco Busan struck the bridge, it ruptured its fuel tanks, spilling over 50,000 gallons of heavy bunker oil into the marine habitat. The physical reality of the San Francisco estuary is highly intolerant of error. Operating heavy industry in a shallow bird sanctuary requires absolute adherence to procedure. The commercial value of these shipping lanes is tied to the environmental stability of the waters surrounding them. They are managed as a single interlocking system. The health of San Francisco Bay relies on consistent, engineered enforcement of these maritime protocols.